Okay, so if this is 2, this is 1, this is 3. At 1, we're at 2.718. That's about right here. At 2, where are you? 7.389. So you come up here. My graph, I'm not going to have enough room. 7.389. And you can get this. And then just come back like that. That's all you have to do. That's the graph of e to the x. Everyone agree? So e to the x is just a specific, it's just a particular exponential growth function. That's all it is. But it's very special, and you'll see it in calculus. Yep. Now, I'm going to change the problem a little bit now. So new problem. I would like for us to do, I'm going to leave that graph up there on purpose. I would like us to do e to the x minus 2. What is that going to do? What does subtracting 2 do to the graph? Moves it what? Moves it down 2. Down 2, because that 2 that I'm subtracting is outside away from the x, isn't it? Just all by itself. So if you graph that, what you would do is you would take everything that you know here and move it down 2. And I'm going to start by taking the horizontal asymptote. Because the horizontal asymptote used to be here, right? That needs to come down 2. So I'm going to move that down 2. This point here comes down 2. This point here comes down 2. And the point up here comes down 2. And so your graph looks like that. And look at, these are just real quick sketches. These are not, they don't have to be perfect. It's kind of like our polynomials and our rational functions. We're just trying to get a general idea of what's going on. Same thing here. Questions? So if you're asked to do this on a test, what you would do first is make e to the x. Draw e to the x. And then just take those points and drop them down 2. Right? That's how you would do it. Let's try a little bit more in here. How about if we do minus 2 up there?
Flips it somehow.
Close.
Yeah, moves it to the right.
That's going to be the one that's a left and right shift. Okay, so do you remember with left and right shifts, it's opposite of what you think? So if it's minus 2, you would think it's to the left 2, but it's actually to the right 2. So we would take the black graph here, right? This black graph, and we would move every point to the right 2. So that means this point here, I go 1, 2. This point here, 1, 2. This point here, 1, 2. What about the horizontal asymptote?
It stays.
It stays. It's still the x-axis. And then I draw. Oh, shoot, I missed that completely. You could easily. Plug 0 in for x, right? Plug in 0, you get what? E to the negative 2. And that would be your y-intercept. Now, I didn't ask this, but on the red one, has your domain changed?
No.
On the red one? No. Has your range changed? Yes. Your y-intercept has changed. On the blue one, has your domain changed? Has your range changed? No. Y-intercept has changed, though, right? All right, let's do another one. What if we do negative e to the x?
That flips across the x.
That's right. That flips across the x-axis. So you're going to take this black function, and you're going to change the sign of it, right? Everything that used to be positive becomes negative. That means every point here gets flipped down. This point gets flipped down. This point gets flipped down. So you can kind of like measure it out and be like, okay, this point goes to here. This distance goes to there. This distance goes to here, right? You thought I was going to do it, huh? And so your graph is going to go like this and come up and still have the same horizontal asymptote. Do y'all see the black one flipped over? It's starting to get kind of messy here, but do y'all see the black one flipped over? All of these different variations were all based upon that first good graph of e to the x, right? From there, it's just a matter of moving left or right or up or down or flipping. Yeah? Another one. How about if I put the negative up here? What does that reflect? The y-axis. That reflects over the y-axis. So that means take the black graph and just goes like that. It goes from growth to decay, exactly. So whatever this distance is, move it over. Whatever this distance is, move it over. This point doesn't go anywhere because it's on the y-axis. All of these points come over here, so it's going to look like this. And your horizontal is over here now. Horizontal asymptote. Yeah? So on your homework, let me just show you an example of one of the problems from the homework. It asks you to graph something like here we go. It asks you to graph one minus 2 to the x plus 3. Draw a quick graph of this and tell me the domain and range. That's what the homework says. So what you have to first realize is that this is negative 2 x to the x plus 3 plus 1. Just write it this way so that you have the exponential part of this out front, the plus 1 out back. How would you go about doing this? First you'd graph, or first you make a table for 2 to the x. All right, so you just identify what's the base here. The base is 2, right? So I'm going to say, all right, make a table. Here's x, here's 2 to the x. Didn't we do that earlier? Yeah. And it looked like that, right? And we had the points, whatever your points are, yeah? That's 2 to the x. Then it's just a matter of figuring out what happens and getting it in the right order. So where do I start in terms of like shifting and reflections? Where do I always start at? With the exponent, next to the x. So the plus 3 happens first. What type of change or transformation is that? Left 3. So I'm going to take that picture. I'm going to go left 3. What comes after the 3? The negative in front. What does the negative in front of the function do? Flip it over the x. If the negative was up top, it would be over the y. So reflect over the x-axis. And then, so I've taken care of the plus 3, the minus 2, and then finally, plus 1, up 1. This right here, I moved it to the back instead of out front. This is a plus 1, right? Positive 1? Right? Isn't 1 minus x the same as negative x plus 1? Aren't those the same?
I thought the entire problem was only negative 2 to the x plus 3.
Oh, no, because of that 1 out front. Okay, so shift to the left 3, reflect it over the x-axis, move the whole thing up 1. That's what I want to do. So let me do it. Everything to the left 3. 1, 2, 3. 1, 2, 3. Something like that. 1, 2, 3. So it's just this picture, right? So far, it's everything to the left 3. We don't have to be perfect, all right? Then take that blue and reflect it over the x-axis, which would be like this now, right? That reflected. And then take that and move the whole thing up 1. So what goes up 1 with me when I move the whole thing up 1? The horizontal asymptote goes up 1 also. So here's my new horizontal asymptote. And my graph all went up 1. So whatever, that's good enough. We're not trying to be perfect here. Because what you want to be able to gather from this is the domain and range. Any questions on the moving around there?
Does it matter what order you do it in? Or?
Yes, absolutely, does matter. You always have to start like order of operations. You start with this first, then you take care of this, and then you move outside. Yes. It does. Let me do it a different way. Yeah, we've done this before where
Some of it makes a difference.
sometimes you get lucky and it doesn't make a difference. Let's see, what if I were to take this, let me move it up 1 first. Okay, so move that up 1. I don't want to mess up my picture. Yeah, if I move it up 1, it's going to be here, right? Now when I flip it, see here's my horizontal. When I flip it, when I flip like this horizontal flips also and comes down here and becomes this. And then when I move that up 1, I'm still below the x-axis, which isn't this. So that wouldn't have worked. Yeah. Okay, so what's the domain of this? All real numbers. What's the range?
Isn't it 1 to negative or negative infinity or 1? 1 to negative. Not negative infinity or 1.
Negative infinity all the way up to 1. With the parenthesis, because I never actually make it to 1. How y'all doing? How you doing? You ready? We're almost done. Okay, you remember how we had to move up 1? That our original horizontal asymptote is right here, the x-axis. I moved the whole thing over to the left, then I reflected it down, and when I do to the left and reflecting, that dotted blue line doesn't move. But when I move the whole graph up 1, that blue dotted line moves up 1. So now when the red function, the highest it ever gets is however high that dotted line is, which is 1. However high that dotted line is. All right, so that we're going to kind of shift gears here for a minute. We're going to we're still in the same section, but we're going to take a look at solving exponential equations. Solving exponential equations. This is a new topic, and I'm going to put here part 1 because we will revisit this later and we will get into harder problems later. But this is just to introduce us to it. All right? All right, so let me just remind you that if I gave you an equation like this, I would expect that everyone in here could solve for x, right? You could either factor it, difference of squares, and then set each one equal to 0. You can move the 4 over, take the square root on both sides. Either way, everyone should get plus or minus 2, right, for a solution to that. And this is what we call a quadratic equation, right? What we're going to look at now are what we call exponential equations, and unless you've seen this in another class, this is the first time you've ever seen something like it. So let's take a look. How about solving this? 5 raised to the 2x plus 1 equals 1 over 125. what you should notice to begin is that the variable that we're trying to solve for is x, but where does it live? It lives in the exponent. And this is really kind of the first time you've ever seen this. Every other time you've tried to solve for x, it's always been down in the base. And so all we've done is just like basic factoring or moving things around the equation. And when we do things, moving things properly, you'll get x equals and then something, right? For this, the x is up here, so how in the world are you going to get this down? Okay, well, you can't, remember there's part 1 and 2, right? You might be thinking part 2, because part 2 makes it easy. Okay, we're going to act like we don't know part 2 yet. So, do you understand, at least appreciate the fact that x is up in an exponent? And so, to get it out of there would be kind of possibly an issue. All right, so let me see if I can't help you with this. Maybe what we do for now is we say, we'll come back to it. Let me give you an easier one, because that one's a little hard. Let me give you an easier one. How about this one? So we'll hold on this for a second. How about this? Solve 3 to the x equals 27. Is that an exponential equation? Yes? Okay. How can you solve that one? Okay. Can anyone just look at that and tell me what the answer is? 3. 3 times 3 times 3 is 27. So you could get that answer just by visual inspection, that if you put a 3 here, you will get that. But that required that you actually know that 3 cubed is 27. This one, you can't just say, oh, sure, x is blah, and that's 1 over 125, right? It's not as easy. So we need a more systematic approach. And so we will do, if possible, we will try and write both sides of the equation with the same base. So can you rewrite 27 as 3 to a power? 3 to the 3, right? You see that? And then at this point, we do not need to go and do anything algebraically. What we need to do is just realize that this, in order for these to be equal, right? For those to be equal, this power has to equal that power, right? Which means x would have to be 3. And that's what you said the answer was, right? X would have to be 3. That's it. Let me give you another one that's a little easier. How about 10 to the x equals 1 over 100? So you look at the left side, you see 10 to the x. Can you rewrite 10 to the x? Can you rewrite the other side as a power of 10? 10 to the negative 2. I'm going to do it a little slower. This is 1 over 10 squared, right? It's 1 over 100. But 1 over 10 to the 2 is 10 to the negative 2, moving it up, right? Moving it up as a negative exponent. Now they have the same base, which means these exponents have to match, so your answer would be negative 2. So negative 2 is a solution to this equation. Do y'all see how this is working? Are there any questions? You sure? We will in a second. How about this? 4 to the x equals 8 to the x minus 2. Oh, whoa. Kind of threw you right into the fire here.
Could you make it less than 2? Like 4 is
You mean over here?
Yes.
Close, very close, good, but not 4 squared, because 8's not 4 squared.
Oh, the 2 cubed?
8 is 2 cubed. So wait, let me go back to this. Weren't we looking at the base here, 10, and saying trying to get a 10 over here as a base? So if you look over here and say I have a 4 as a base, I have to try and write this as 4 to a power. But 8 is not 4 to a power, right? 8 is 4 times 2, but it's not 4 squared or something like that. But these both do have something in common. 4 is 2 squared, and 8 is 2 cubed. Agreed? So I'm going to rewrite this as follows. Here's 4. Everyone agrees that that's 4? And that's being raised to the x. And over here, do you agree that this is 8, which is 2 cubed, but being raised to the what? X minus 2. And now we use the property or the laws of exponents that I put up here earlier. A to the s to the t. We said we multiplied these two. I want you to multiply 2 times x, right? 2x. So this is 2 to the 2x must equal, over here, 2 to the 3 times that is 3x minus 6, right? If I multiply 3 here and 3 there. Now, do they have the same base? Yes? Which means that these two have to be equal, don't they? In order for this equation to be true? So let's write that down. I need 2x to be equal to 3x minus 6. Which means? Yeah, you can add 6, subtract 2. So you get something like this. X is 6. That's your solution. And you could check it, right? Couldn't you check it? Let's check it. 4 to the 6th power needs to be equal to 8 to the what? 4th power. So plug in 6 here and 6 here. Is that true? So on your calculator, is 4 to the 6th the same as 8 to the 4th? Yeah, maybe. Sure it is.
Yes.
Okay. That takes a little bit of imagination, okay, to get those two sides to have the same base. Let me give you, let's go back to the one that we quit on. It was 5 to the what? 5 to the 2x plus 1 equals 1 over 125. Now maybe now this one will seem a little easier. This side over here, 125 is 5 cubed. So if we bring it up, it would be 5 to the negative 3. So we have 5 to the 2x plus 1 equals 5 to the negative 3. Everyone see that the right side is 5 to the negative 3? Then 2x plus 1 equals negative 3. So you're matching these up. As soon as the bases are the same, you can do that. So x is negative 2.
Yeah, I think I'm thinking of what
Yeah, you are. Because what I'm about to show you now, we'll see we're going to run into a problem. Right? Y'all see this? Y'all comfortable with it? I'm going to give you another example of this. And then I'll get to what Lily's talking about. How about 9 to the 2x times 27 to the x squared equals 3 to the negative 1. That squared right here is only acting on the x. It is not this. See, these two are different things, because this right here would be 27 to the what? 2x. See the difference? This is actually 27 to the x to the x. That's what that is. Because you do these two multiplied, that's x squared. See the difference? Okay. But let's get back to what we're trying to do here. This is an exponential equation. The exponent has the variable in it. So we need to somehow try and get these things to match on both sides. 3, does everyone see the base 3 is common to all of these? So I'm going to rewrite 9 as 3 squared. I'm going to rewrite 27 as 3 cubed. And then the right side 3 to the negative 1. And this is multiplication right here. What is 3 squared to the 2x? You multiply these two together, right? 3 to the 4x times, now what's 3 to the 3, all that to the x squared? 3 to the 3x squared, and then equals 3 to the negative 1. Now what? Well, what we had been doing before is we had been trying to match the exponents, right? We can't quite do that yet because this is not a single 3 to the something, right? But can you put those together? Right? They have the same base, different exponents, so what do you do with that? You add. It becomes 3 to the 4x plus 3x squared equals the other side 3 to the negative 1. Y'all told me this earlier, that if I had a to the s times a to the t, that it was a to the s plus t. That's what y'all said earlier. Y'all agreed with me on that. And that's basically what I have here. I have a to the s times a to the t is a to the s plus t. Now can I just match up the exponents? Yes, this and this have to be equal in order for those two sides to be equal. And that's a quadratic equation once I write it down. So I'm going to write down 4x plus 3x squared. That needs to be equal to the other side, which is negative 1. And we recognize that's quadratic equation. We move everything to one side, and we do whatever we need to do. So 3x squared plus 4x plus 1 equals 0. And then maybe factor. 3x plus 1, x plus 1. And you get two answers. Negative 1/3 and negative 1. There's actually two solutions to that. Okay. Now, let me just give you kind of an idea of where we're headed with this, all right? The main idea in this chapter is to be able to solve equations that involve exponentials. The graphing of exponentials is important, but it's not like the main idea. It's not the main point. This solving of an equation that we just did is more useful later to us. So we're kind of stepping away from the graphing as being the most critical thing, all right? With that said, I want you to take a look at one last one and tell me what you think. So try and solve this. 5 to the x equals 7 to the 2x minus 1.
Well, can you multiply them to get this one? Or to get the same base?
How do you mean? Oh, you mean like try and get like common base of 35 or something? Think about that for a second. If I multiply this by 7, right? I can't put these two together. Order of operations always requires me to figure out what this is before I put this together. Right? Exponents has to happen before multiplication. So you can't just multiply that and get a 35. All right? It's a good observation, but we couldn't do it. All right, so what we did before is we tried to find the same common base in both of these, right? Like 2. Here, you can't find a common base. There's only one base for 5, and that's 5. And there's only one base for 7, and that's 7. So the question is, how do we solve that? We have to have a better way of doing it.
Do we have to put it in there somewhere? Maybe use E?
Well, we won't use E. What we're going to do next, okay? What we're doing next is this. We're going to step away. We're going to kind of submit to this, wave the white flag at this, and say, look, we can't do this, but I'm sure there's a way to do it, right? And what we're going to do is now come in with looking at the inverse of an exponential function. So if somebody gives you an exponential function, right, we graph it. We know what the graph of exponential functions look like. This is what we're going to talk about next class. An exponential function looks like this, or it goes the other way. Is this a one-to-one function? Yes, passes both the vertical and horizontal line test, which means it must have an inverse. What is the inverse of an exponential function? Well, those are called the logarithmic functions. The logarithmic functions are the inverses of the exponentials. And once we get our heads around what the logarithmic functions look like and what they do, we're going to see that when we put a log function together with an exponential function, what should happen? They should wipe each other out. And these log functions are going to have a lot of properties to them, and that's what we will actually use to address this. But we have to use the inverse of the exponential function to do it, which we haven't talked about. So that's what next class will be. And then eventually I'll come back to that and we'll solve it, and it won't be that big of a deal. All right? So do your homework for 6.3 and have a good weekend, right? It's Wednesday, so have a good weekend. I'll see you on Monday. I will try and get everything graded. I said try.